Now that we finished integral calculus, we have the necessary tools to check to see if the world's most famous equation, E equals mc squared, is mathematically consistent. We're going to derive each side of the equation separately. Let's start with the left-hand side. We know that energy is also equal to force times distance. Writing this in simple algebraic form, we have E equal to F times D. Because the real world is more complicated, we need to rewrite this energy equation using calculus. How much energy a system has is represented by the integral of the change in energy, written as dE, equal to the integral of force times the change in distance, written as d of d. Notice that the force variable doesn't have a d in front of it. Since force is also subject to change in the real world, we will need to transform this variable. Thanks to Newton, we know that force is also equal to the change in momentum, written as d of d, divided by the change in time, d of t. Momentum can be further broken down into mass times velocity. We now can do the product rule of m times v, which is equal to dm times v divided by dt plus m times dv divided by dt. We can insert this adjusted force variable to our main equation, but we will switch the order since it will be easier to read. This is all being times the change in distance. In this next line, we distribute the d to the product rule of m times v. We will also integrate the d so it just becomes e. Now we're going to shuffle the dt that is in the bottom of the product rules and put it underneath the change in distance, d of d. The d of d divided by dt is just the v, velocity. We will rearrange and distribute the v. We finally have energy equal to the integral of mv dv plus v squared dm. Let's now leave the left side of the equation and begin work on the other side of the equation. The right side of the equation starts with Einstein's brilliant use of the Lorentz transformation, where the mass of an object is equal to the rest mass divided by the square root of 1 minus v squared divided by c squared, which just means that the faster you go, the heavier you will be. We will then take the derivative of this equation in respect to the velocity. But before we do that, let's algebraically rewrite the radical and bring it upstairs as a negative 1/2 power. Taking the derivative of the mass, we get dm divided by v. Using the chain rule to the right-hand side, we bring the negative 1/2 downstairs. We leave the inside alone, subtract the power by 1, and times that by the derivative of the inside of the parentheses, minus 2v divided by c squared. We can cancel the negative 1/2 with a negative 2. We then reshuffle v divided by c squared and put it next to the m0. We then split the negative 3/2 power into negative 1/2 and negative 2 over 2. The negative 1/2 power is just rewritten as a radical in the denominator, and we create common denominators with the 1 minus v squared divided by c squared into c squared divided by c squared minus v squared divided by c squared, all raised to the negative 1 power. Since the denominators are the same, we can combine the two fractions. With a negative power, we can turn it positive by flipping the fraction. After moving the square root to the front, we see that we can cancel the c squared that's attached to the mv with the c squared of the flipped fraction. Notice that the m0 divided by the square root of 1 minus v squared divided by c squared is the equation we started with, so we can just rewrite this as blue m times v divided by c squared minus v squared. We can cross multiply the fractions. On the left we will get c squared minus v squared times m dm, and on the right hand side we get mv times dv. On the left we will distribute the dm to c squared minus v squared and then add the v squared dm to the right hand side of the equation. We now can take the integral on both sides. The integral of c squared dm is just mc squared. We actually don't need to take the integral on the right hand side of the equation because you will notice that it's the exact same as the right hand side of the energy equation we derived earlier. So therefore, E is equal to mc squared, showing that the equation is mathematically consistent. So we didn't go over Einstein's brilliant logical deductions that discovered this equation. This will require the understanding of conservation of energy and momentum. We also didn't cover the direct implication that mass is just another form of energy, and energy is just another form of mass. To truly appreciate this equation and all the other insights from Einstein's paper on special relativity and general relativity, we need a couple more math classes besides calculus. You will need differential equations, tensor calculus, and differential geometry.